Morning and afternoon to all of you. If you're joining from Australia, um, I would like to thank you for attending today's webinar on reinforcing foundations with geosynthetics. My name is Abid Ali, and I work as a senior applications engineer with Geofabrics. Just to remind all of you that if you've got any questions, please feel free to send them to the question and answer chat box. And the webinar will be recorded and will be available in a week's time. So I'll start with the webinar now. So in this webinar, I'll give you a brief overview about Geofabrics, and we'll also see some selected functions of geosynthetics. And we'll also look at geosynthetics, which are relevant to today's webinar. And the main theme of today's webinar is to showcase several case studies where geosynthetics were used instead of traditional methods. So case study one, where geocell and woven geotextile was used in a reinforced shallow foundation for a large culvert slab. Then case study two, where a working platform was proposed for a large crawler crane comprising multi-axial geogrids stabilized layer on a geosynthetic cellular foundation mattress. In case study 3, we'll see the use of multi-axial geogrid stabilized working platform for a large ringer crane. In case study 4, we will see how geogrids were used to design a shallow foundation for a large storage tank. And in case study 5, we will see how woven geotextiles were used for a large storage tank. Now, case study 1 is a project which I have worked on personally, but the other case studies are overseas projects, and information about them is available in public domain. So Geofabrics is Australia's leading geosynthetic supplier and manufacturer. We have been around for more than 4 decades. We've got 2 manufacturing sites, one in Ormeo in Southeast Queensland and one in Albury. We also have 12 offices throughout Australia. Geofabrics has the GRID, which is the Geosynthetics Research, Innovation and Development Department on the Gold Coast, which also includes the technical team, and I'm part of the GRID. And at Geofabrics, we provide solutions for several sectors such as infrastructure, mining, waste and containment, to name a few. All right, let's look at these functions of geosynthetics pertinent to today's presentation. So the first one is separation, and these definitions have been taken from ISO 10318, and separation basically means that a geosynthetic is used to separate dissimilar material. Then we have filtration. In filtration, not only separation comes into play, but also the geosynthetic is required to prevent passage or loss of material from one layer to the other one. The geosynthetic also protects or prevents any uncontrolled passage of material through it. Then we've got reinforcement, where the geosynthetic basically acts as a structural material, and it provides benefit to the soil or the structure it is placed in with. And then we have stabilization, where again the geosynthetic is adding structural benefit to the application it is used in. In reinforcement, the tensile strength and stiffness are important, whereas that is not important in case of stabilization, because in stabilization, The geosynthetic basically laterally confines the aggregate and improves the properties of the aggregate. Now let's look at relevant geosynthetics. So in today's case studies, we will be seeing how these geosynthetics were used. So we've got multi-axial geogrid, we've got GeoWeb or GeoCell, then we've got a woven geotextile, we've got uniaxial STP geogrid, and coated polyester geogrid. So these geosynthetics were used in the case studies that I will be presenting now. So let's look at the first case study. So for a commercial development, two large culvert slabs were proposed. The dimensions are given here, so they're quite, I would say, decently sized. Geotechnical investigation revealed presence of soft foundation and also potentially environmentally hazardous soils. So initial recommendation was to adopt pile foundations due to the size of the structure and also due to poor ground conditions. But the client was keen on exploring an alternative solution using geosynthetics. So we worked with the client's geotechnical engineer. They provided us with the ground model, and we did some initial numerical analysis to determine the bearing capacity of the ground without any platform and geosynthetics. So the subgrade was obviously weak and it was not able to meet the required bearing capacity. So we worked with the supplier and we came up with a solution as shown over here, where the bearing capacity was determined analytically, and we proposed this to the client. And the total platform thickness was less than 10% of the largest slab width. So the construction was quite straightforward. The woven geotextile was placed on the subgrade first. So this one provides separation, filtration, reinforcement as well. And so this was placed directly on the subgrade, and then the base layer was constructed. Then the first layer of GeoWeb was placed. Then an intermediate layer was placed, and then the second layer of GeoWeb was placed. The geosynthetics were extended 2 meters beyond the edge of the slab on either side. So here are some more photos from the construction stage. Here we can see the GeoWeb being placed, and here you can see pondered water as well. So obviously the ground conditions are not quite favorable. And then here we see the photos after the construction of the concrete slab. So the foundation is placed over here. And then we visited the site a year and a half after construction, and we noted that the culverts are performing quite well. So these are the photos taken from that site visit for culvert 2, and these are the photos taken for culvert 1. And then we also visited the site just recently, which is nearly 3.5 years after construction, and the solution basically continues to perform well. So the next case study is from overseas. Now in this case study, which is for an offshore fabrication yard in Vũng Tàu, Vietnam, a solution was required to support a 1,300-ton crawler crane, which had 2-meter wide tracks spaced 7.6 meters apart. Now, the track exerted a bearing pressure of 400 kPa, and the track dimensions are shown over here, so quite a big track. The foundation consisted of soft clay with an average undrenched shear strength of 23 kPa over a depth of 10 meters. The initial design recommendation was for deep foundation solution. However, an alternative option was proposed to the client, as shown over here, which basically comprised a working platform with a combination of multi-axial geogrid to form mechanically stabilized layer on the top, and then a geosynthetic cellular foundation mattress at the bottom. So this solution was expected to help distribute the loads from the crawler crane more efficiently to the foundation and provide a safe surface for operation of the crawler crane. Now, the design was done to reduce the pressure at the base of the foundation mattress to an acceptable value. Or in other words, you can say to have some sort of a bearing capacity, factor of safety against bearing capacity. So the pressure at the base of the foundation mattress was calculated as 64.5 kPa, which gave a factor of safety of 2 for the bearing capacity. The geogrid grade required to construct the cellular foundation mattress was calculated using this equation proposed in Jena et al. And based on this suitable uniaxial geogrid, I should say HTP geogrid, was chosen to meet the required tensile strength of 33 kilonewtons per meter. So in terms of construction, the multi-axial geogrid was first placed directly on the subgrade. Here's the photo from the side. And then the 1 meter high foundation mattress was fabricated on site using a combination of transverse and diagonal diaphragms or members made up of HDP uniaxial geogrid to form closed cells, as we can see over here. The nodal connection was formed by passing folded diagonal ribs through the transverse apertures to form loops, and then these were held in place by using a nodal connector. Now, the cellular foundation mattress was filled in stages, as shown over here, with 75 mm minus well-grade aggregate. And once the construction of the foundation mattress was complete, the MSL was constructed using multiple layers of multi-axial geogrid and the same aggregate. The first layer of the geogrid was placed 200 mm above the foundation mattress, and then we had 4 layers 400 millimeters thick, and the topmost geogrid was placed 200 millimeters below the surface. To assess the performance of the working platform, a plate load test was undertaken, and the performance target was less than 100 millimeters at 500 to 600 kPa pressure. A special steel plate was fabricated to carry out the plate load test, and pressure was applied using 6 jacks, which were nearly equally spaced, and there were 6 dial gauges as well to record the settlement of the plate. And a cartilage of 1100 tons was used to provide the required reaction force for the jacks. So the loading was applied in 100 kPa increments, and the settlement after applying 600 kPa was around 41 millimeters, which was well within the required settlement criterion. And later on, a back analysis was also undertaken using 3D final element analysis, and a very good agreement was obtained between the field test results and the numerical simulation. Now, Let's look at the case study where only multi-axial geogrids were used for a working platform. So this is for a petrochemical facility in Southwest Louisiana, where this ringer crane was proposed. Now, this ringer crane had pretty massive dimensions. It had a 56-meter outside diameter and 33.2 inside diameter. And it imposed a pressure of 192 kPa over its footprint. It was the third largest crane in the world, and it had 3,500 tons of counterweight and a capacity of undertaking lifts of 975 tons at a 74-meter radius. And it was also used for undertaking 62 heavy lifts, including 688-ton watchtower. So the ringer crane was supported on 11.5-meter wide circular track, as we can see. There were stringent requirements for differential settlement. The variation over the outside diameter should not be more than 0.1%. And site investigation comprised one borehole to a depth of 30.5 meters, indicating high plasticity clays over nearly half the investigation depth. The groundwater table was also shallow, between 1.2 to 1.8 meters, and undrained triaxial tests on samples indicated shear strength of 32 to 79 kPa, increasing with depth. So for this particular crane, the original design comprised 200 concrete piles to 20 meters, 61-meter pile cap, and construction cost of 2.7 million US dollars, demolition cost of 0.6 million US dollars, and total cost of 3.3 million US dollars. Now, the parameters for alternative design were a bearing pressure of 295 kPa, subgrade stiffness of 6.5 kg per cm cube, and differential settlement should be less than 1 in 100. So an alternative design comprising mechanically stabilized working platform with 5 layers of multi-axial geogrid was proposed. So this working platform was 17.5 meter wide and 1.83 meters thick. So for settlement analysis, the crane footprint was considered to be pseudo-rectangular, as shown, and 3 additional locations were considered for determining the different, which basically helped in assessing the differential settlement. So one was the midpoint along the long side, midpoint along the short side, and then the corner. So based on the information available, we calculated the average differential settlement, and it was less than 0.5%. And non-stabilized aggregate of same thickness as the platform would have had 36% greater overall settlement and 44% higher differential settlement. The actual settlement during crane operation was expected to be much lower, and the reason for that was because the crane will be operational only for a short period of time compared to the time required for primary consolidation settlement. So to construct this working platform, the subgrade was proof rolled. Any soft spots were over excavated and replaced and compacted. So the first lift thickness was 460 millimeters, after which the first layer of geogrid was placed. And then there were 3 layers of 305 millimeters, and the last 2 layers were 230 millimeters. And each geogrid layer was rotated by 60 degrees with respect to the layer below, as shown. And plate load test was conducted on lift 3 to determine the subgrade support using 457 millimeter plate with loads gradually increased to 450 kPa. And the ground stiffness values were higher than what was required. An aggressive drainage system was also designed for the working platform to keep it well drained. And for the sake of brevity, I have not presented that, but a lot of detail has been given about the drainage system. And once the crane had been set up, the site was hit by Hurricane Harvey. And after the crane had passed, after the hurricane had passed, the crane could resume the lifts the very next day due to the benefit of a very good drainage system and also due to the mechanically stabilized working platform. So this photo basically shows the ringer crane lifting a 100-meter high watchtower, which weighs around 688 tons soon after the hurricane had passed the site. It just goes on to show how well the platform was performing. The observed differential settlements were much lower than what was stipulated. So the initial cost of the pile foundation was around $3.3 million. Installed cost of mechanically stabilized working platform was $1 million. Cost saving of $2.3 million. And crane lifts were completed 32 days ahead of schedule, which helped the client save some additional money. And Memo had stated that the geogrid stabilized platform was a new standard for the crane pads. Now let's look at a case study where geogrids were used for a shallow foundation for a large storage tank. So this case study is from Canada, where 2 large diameter storage tanks were proposed on the harbor side of on the south side of Hamilton Harbor in Ontario, Canada. Now this site is basically a reclaimed land. And the bearing pressure over the tank footprint was around 120 kPa. And geotechnical investigation on the site revealed presence of medium dense fill near the surface, so approximately around up to 2-meter depth. And under that, there were very loose sandy silt and silty sand, so very low SPT blows. And that was underlain by silty clay silt, which became firm with depth. And then bedrock was at a depth of 26 meters. So this profile is taken from one of the boreholes during the site investigation. Now, due to poor ground conditions near the surface, intensity of loading, and the footprint of the tank, initial designs basically called for either end-bearing piles or ground improvement using stone columns. And due to the high cost associated with the above solution, the owner was inclined towards a shallow foundation solution. So steel storage tanks are quite tolerable to differential settlement, and historical records indicated that the southern portion of the site was loaded with large aggregate stockpiles up to 10 meters high, which indicated that the site can support substantial surface loads without significant failure. So an additional geotechnical investigation was undertaken to supplement the available borehole data, and 3 DMT soundings were carried out over the site, and information that was available indicated that the results of DMT soundings can be used to obtain reliable settlement estimates. So settlement analysis was undertaken using numerical tools and verified using hand calculations. The constant modulus obtained from DMT was considered for settlement analysis carried out using numerical tools. The settlement obtained was around 55 millimeters at the south, which was possibly preloaded, 130 millimeters at the tank center, and then 80 mm towards the northern end of the tank. Now, the DMT soundings indicated that the OCR was less than 2 in the upper 8.5 meters, and beyond that, it increased to more than 4. So, for settlement analysis purposes, only the top 8.5 meters was considered, and for the northern end, the hand calculations indicated a settlement of 72 millimeters. Now, geotechnical investigation also indicated that the fill near the surface was granular in nature, and PhDs on that material showed that the material could, if it's carefully excavated, it could be reused to construct the granular pad. So, and stability analysis was also undertaken using 2 layers of mirror grid 5XT, and that indicated that the required factor of safety could be achieved. And the benefit of geogrid reinforcement on bedding capacity was determined using the FHWA approach, and that met the required design criteria. The geogrid reinforced pad basically then comprised a 1.5 meter thick platform with 2 layers of mirror grid 5XT, which is a coated polyester geogrid. And the geogrids were placed at the bottom of the pad and spaced 300 millimeters apart. So to construct the pad, the following steps were taken. First, the excavation was done up to the base of the pad, followed by dense compaction. Then the geogrids were placed at a radial pattern as shown, and these were extended 3 meters beyond the wall footing. And then the first lift of granular material was placed, approximately 300 millimeters, and well compacted. Then the second layer was placed, and then the remaining thickness of the pad constructed using side-grown material. So post-construction monitoring indicated that the settlement at the northern end was less than what was initially estimated. So it was 54 millimeters compared to the 80 millimeters initially estimated. And that at the southern end was around 41 millimeters, less than 55 millimeters, which was initially estimated. So these numbers are taken a year after monitoring the site for settlement. And here are some photos showing the placement of the geogrid and the construction of the granular pad. And this brings me to the last case study, another large storage tank, and also in Canada. But this time the tank had a slightly large diameter of around 40 meters, and it imposed a pressure of 175 kPa over its footprint, so much higher pressure. And the geotechnical investigation basically indicated presence of organic topsoil near the surface, and presence of soft mixed lacustrine clay to a depth of 6.1 meters. And then this was underlain by silty sandy clay to depths greater than 15 meters. And there was a 3-meter thick band of wet silty sand layer at 7.5 meters. Groundwater was also observed at a shallow depth of around 2.6 to 3.5 meters after the geotech investigation. Now, due to the presence of poor ground conditions and high water table, embedding piles would have to be at least 10 meters deep. The site owner wanted a cost-effective solution and decided to proceed with a geosynthetic reinforced foundation instead. So the bedding capacity check was undertaken using LRFT method, and global stability and settlement analysis were conducted using computer-aided software, and hand calculations were also carried out to determine the consolidation settlement. So the soil layer thicknesses and the properties that were assumed in the computer model are shown over here. And the factor of safety for global stability was around 1.8, and the maximum settlement at the center of the tank was around 150 millimeters. And out of this, 129 millimeters was in the top soft clay layer. So during the construction of the tank, its perimeter was divided into 14 survey stations. So station 1 was located at 355 degrees with respect to the north, and the subsequent stations were numbered clockwise. The distance between two stations was approximately 8.9 meters. And these stations basically served as reference points for monitoring the total and differential settlement of the tank. During construction, black organic material within the lacustrine clay was observed, which was as expected. And they also came across a soft saturated subgrade zone between stations 9 to 12. And so this area was remediated by over excavating 3 meters, and then they filled 2 meters of granular material uncompacted, and then placed additional granular fill and clay layer, which were then compacted to form the subgrade in this portion. So once the soft spot or this area was remediated, the top 300 millimeters of the exposed surface was cement treated to form the base of the REF. And a 3-meter thick reinforced earth foundation was constructed using 8 layers of Merafi RS580R at 375 millimeters apart. So each layer of RSI was placed perpendicular to the layer below. Now, after the tank was constructed, load test was also carried out, but it was expected, due to the presence of the permeable silty sand layer at 7.5-meter depth, that the consolidation settlement will occur quickly. So the tank was basically filled in stages over 12 days and surveyed as per API 650 guidelines. Now, after the construction of the reinforced earth foundation and prior to loading, the total settlements varied between 34 to 70 millimeters along the stations, and there was a differential settlement of 13 millimeters, so which is quite reasonable. Now, once the tank was loaded, the settlement increased to 74 to 150 millimeters, and when it was unloaded, there was some rebound, and then the total settlement decreased, and it varied from 54 to 122 millimeters. Now, the maximum differential settlement after the hydro test was 15 millimeters, which was slightly above the API guidelines, but it was considered acceptable for this particular project. And between station 9 to 12, there was greater settlement, and that was due to the uncompacted lower backfill in the remediated section. And some of the stations experienced reduced settlements, and that was due to the compaction caused by repeated truck loading along the access ramps for constructing the REF. Overall, the REF performed satisfactorily, as the measured settlements and was considered acceptable, although the differential settlement exceeded the allowable value slightly, but it was still considered acceptable for this particular project. So these case studies basically demonstrate that by using geosynthetics, a cost-effective solution can be achieved compared to more traditional approaches. And in using a particular geosynthetic type, it is important to understand how it performs so that its benefit can be accounted for properly in the design. And a proper geotechnical investigation and understanding of ground conditions is a must. So without a proper understanding of the ground, it will be difficult to come up with a very good design. And lastly, I would like to take the opportunity to also showcase our technical support areas. So we can provide you with assistance for pavement design, working platforms, rail track bed, basal reinforced embankments, and slopes and walls. And we also have capability to assist you with numerical analysis as well. So these are my contact details. If you got any projects or if you got any queries related to the webinar, you can reach out to me. Thank you. And these are the references for today's webinar. So thank you for your attention. And I'll just stop sharing and go to the question and answer chat box. All right. So how do you assess the impact of groundwater table on the application and adjust the design as required, if any? Well, the simple thing is that if you're talking about this impact on the platform, so the platform will have some reduced bearing capacity due to the presence of the groundwater table. And yeah, so that will have to be basically adjusted or accounted for in the design. And the other question that is, can we get a link to the recorded webinar? Yes, the webinar will be available in a week's time. So please feel free to log into Geofabrics Academy next week, and you should be able to access the recording. I'll just wait for a few more minutes. If anybody's got any questions, they can type in the questions through the question and answer chat box. Okay. What is the angle of load spread line for the geocells? So I'm assuming that you're referring to the case study 2. And based on the information available in the publication, load spread angle of sorry, if it's a geocell, then we can use a load spread method. We use an analytical method for the case study 1. And how did the next question that I have is, how did they compact aggregate within the geocell? So based on the information, it looks like they basically placed, you can spread the aggregate into the geocell, and it looks like they just compacted it with the construction equipment they had on site. I was not there during the construction, but we had provided all the required technical documentation to the client to help them understand how to construct the platform. Okay, we've got one more question. Is there any application on areas with steep slope with ferrosol, with steep slope having a high risk of landslide with ferrosol clay dominated or weathered basalt? I don't know of any case studies, but having said that, we may probably just need to check and see if any sort of project is available. All right, it looks like we don't have any further questions. So thank you all for attending today's webinar. and I hope you enjoyed the webinar. Okay, we do have actually. Can we use this to minimize differential settlement for extended bench in substation? The original bench was built over 20 years ago, and the substation is sitting above a 7-meter compressible layer. Yes, geosynthetics can be used to minimize differential settlement. Unfortunately, I can't shortlist any particular geosynthetic without knowing what the geometry is like. So it would be best for you to contact us, and then we can discuss more about your project. Can it be used to consolidate soil in areas with steep slope? I'm not too sure. I am able to answer that questions. If you like to contact us directly, that would be better. Then we have another question. Is there any application at dam settlement? Well, the geosynthetic cellular foundation mattress is used to control differential settlement across the embankments. So it's a common application. It's called basal mattress, and it helps control differential settlement in embankments. All right, then. Thank you, everyone, for your attention. And if you got any further questions, please feel free to reach out, and we'll be happy to assist. Thank you.